Hey everybody, so my apologies, my video cut out there for a second, so let me just run back through here. Independent and dependent, we'll get into more of these in a little bit later, but in a nutshell, if they're independent, then one thing happening does not affect on the other one. So if the probability of B given A, so probability of B saying A already happened, is the same as if A didn't happen. So it's the same as just B. So likewise the other way around. So A given B, so the probability of A knowing that B already happened is the same as if A just happened by itself. So B didn't happen at all. So in that case, they have no effect on each other. And dependent is kind of a catch-all. Anything that's not dependent is independent. And these are I said that backwards. Anything that's not independent is dependent. And it's kind of a catch-all term. So this is kind of our important one. This is kind of our normal one. Okay. So the multiplication rule itself, it's the probability of A and B. Okay, and kind of your keyword there. In general, the probability of A and B is equal to the probability of A times the probability of B given A. Okay, so we explored that a little bit yesterday, so you can play around with that as we go through here, but we'll work some out here in a minute. If it's independent, so you know they don't affect each other, so you have drawing a card and rolling a dice, no effect on each other, so they're independent. You can simplify it to just the probability of A times the probability of B. You don't need that given thing in there. Okay. So let's try out a few of these and see how they go. So a manufacturer claims that keyboards it sells are defective at a rate of only 0.015. So what's the likelihood the first two keyboards you unpack being defective? Okay. So as we go through here, we have two of them. So this one is a little bit different than here because look at it, we're doing the same thing twice here. So if we're going off of their claim here that this is the defective rate, but the two keyboards made by the same person, it's actually a little bit easier. So we're just looking at, are these affecting each other? And we're going off the assumption here of no, there's completely separate keyboards. So it's going to be the probability of the first one's defective. I almost missed a zero there. 0.015 times the probability that the second one is defective. Okay. So probability of A times the probability of B. Grab our calculator, pop it in there. .015 times 0.015 land you at 0.000225. All right, down here, your team is down 2 points. Your star shooter is on the line, and she averages 80%, so she was shooting 3 free throws was the probability that your team will win. Okay. So in order to win, if we're down by 2, she needs to make all 3 of them. So she averages 80%. So once again, assuming these are independent, and she has a little routine so that if she misses one, it doesn't throw her off, then you can assume, make sure you switch this to a decimal. We have 0.8 times 0.8 times 0.8. So she needs to make all 3 of them. So I need success for all of them. So 0.8 times 0.8 times 0.8, 0.512. So a little over a 50% chance we're going to win if she makes all 3 of them. Okay. All right, moving down here. 2 cards are selected from a deck of cards without replacement. Find the probability of selecting a king and then a queen. Okay, so the first one is a king. So we're doing and here. So the probability of the first one is just the probability we get a king. Okay, so just write this out formula-wise because this one is dependent, so it's a little bit weirder. So the probability we get a king times the probability that we get a queen given we got a king on the first one. So that's my probability of A and probability of B given A. So numerically, this one's easy because it's just normal. So there are 4 kings out of the 52 cards in the deck. And then here, this is what we looked at. So we already pulled a king out. So how many queens are left? Still 4. But how many cards are there after I pulled out that first king? Now we're down to 51. So we have 4 over 52 times 4/51, which is a very small number. So notice you get to the E here, and this will happen on the graphing calculators as well. You'll say E something at the end. Anytime you see that, usually you want to avoid writing a decimal. So how I'm going to get around that is I'm going to multiply straight across. So 4 times 4 is 16. And then I'll do 52 times 51, and that's going to be my denominator there of 2652. All right, and as I say this, it looks like I'm actually just losing some pixels here. So let me double check. Yeah, so that is the same spot. So it looks like that actually was supposed to be an 8. So if you wrote 0.006, that's totally fine. So, because that's not an E. My fault. Can't trust any old calculator. But that's okay. Either way, this or, I just forgot what I said, 0.006. Either of those are perfectly fine. All right, moving right along here so you guys can get to your worksheet. So a coin is tossed and a die is rolled. What's the probability of getting heads and a 6? So as I mentioned when we went through the notes up here, the key example of being independent is when two things don't affect each other at all, like a coin and a die, or a die and a card, or something like that. So these are independent. So the probability of getting a heads is 1/2. The probability of getting a 6 on a 6-sided die, it doesn't tell you how many sides. Remember, you do assume that there are 6. So the probability of getting a 6 is 1 out of 6. So I'm going to go to my independent one and just multiply them together. So I end up with 1/2 times 1/6 and end up with 1/12, or approximately 0.083, or 0.83 repeating. If you don't want to round, you can put that repeating symbol over it. Okay. These are very similar on the back. The only difference is we do get some tricky phrasing here. So at least, please be careful, okay? I'm going to go into all the different types later. Right now, I just want you to kind of think through on yours, what does it mean, okay? So going into example 3. So the probability of a fish swimming successfully through a dam is 0.85%, okay? Apparently, this one's made for fish. So if 3 fish are trying to swim through the dam, what's the probability that all 3 are successful? Okay, so let's think about this. If 1 is successful at 0.85, I need to do that 3 times. So anytime you're repeating the same thing like we were on the front, you can absolutely write it like this. Okay, but since we have that repeating, we can straighten it up a little bit and neaten it and just raise it to the 3rd power. Those are both the same thing, so whichever one makes you more comfortable, you're welcome to do that. So either way, you should end up with 0.614, and then I'm going to round it there, leave it there. 6.14 or 6.614125-ish, but we're going to leave it at 3. Okay. So the probability that none of the 3 fish are successful, this is a complement, so this is the opposite. So the complement here of 0.85 is 1 minus 0.85, which is 0.15. So here it's 0.15 cubed. Okay. So please be very careful here that you do the 1 minus to the original probability here. Every once in a while, I get someone who tries to do 1 minus from this one, but the opposite of all 3 making it is not none of them making it. Remember, you could have 1 or 2 or 3 or whatever. So make sure you do the complement to the original one. This is where our tricky wording comes in. At least 1, okay? So 1 fish or 2 fish or 3 fish, that's going to be the opposite of no fish. Hold on, my lights are turning off. Silly classroom lights. Okay, so this is where you can actually save some time and do the complement of this one. Okay, so this is where you can say 0 minus, or 1 minus 0.03375. which lands us at 996625. Okay, so stretching this one out a little bit just because there's so many zeros, I didn't want to call it 003. But, okay, so opposite of none is at least one, not all of them. Important distinction as we go through here. All right, last example, very similar to the ones we already looked at. So 5 quizzes this grading period. The probability you pass is 80%. What's the probability you pass all 5? You need an 80%, and you need that 5 times to get all 5. So you just raises it to the 5th. And you get 0.32. I'm going to round to the third one again, 328. All right, 7 quizzes this period. What's the probability you fail all 7? So this is the complement. So if the probability you pass is 0.8, the probability you fail is 0.2. And now there are 7 in this example instead of 5, like there were here. So 0.2 raised to the 7th. Good news for everybody. I'm going to actually keep all of these in here. 0, 0, 0, 0, 1, 2, 8. So not likely at all, which is always good. All right, this one has 6 quizzes. What's the probability that you pass at least 1? So that at least, okay, is going to be a complement. So at least 1. Remember the opposite, like we talked about in the previous one here, is the complement of none. So I'm going to do 1 minus, what's the probability we pass none of the 6, which is 0.2 to the 6th power. So probability of failing raised to how many times of doing it raised to the 6th. And you can actually enter that directly in your calculator. So 1 minus 0.2 raised to the 6th. And it'll do it all for you. If you don't want to do this, then plug it back in as 1 minus. So 0.999936. And there you have it. Playing around with some of the multiplication rules and complements and all sorts of stuff. All right, so good luck. And if you have questions, just let me know tomorrow.